Welcome back. In the previous video you saw logistic regression for linear classification. In this video you will see how to use a linear classifier like logistic regression together with some nonlinear features in order to do nonlinear classification. If you didn't yet watch the previous video where we talked about logistic regression for linear classification, then please go ahead and watch that video before continuing. Here is a quick reminder about what we saw in the logistic regression lecture. The hypothesis function parameterized by the parameters vector theta is defined as h of x equals to g of theta transpose x, and g is our logistic function or sigmoid function. Right? It's defined as 1 over 1 plus exponential minus this argument a, which is basically theta transpose x. And this function looks like this. So for values of theta transpose x which are positive, this function gives you values or output between 0.5 and 1. And for values of theta transpose x which are negative, this function outputs values which are between 0 and 0.5. When theta transpose x goes to minus infinity, this function goes to 0. And when it goes, theta transpose x goes to plus infinity, this function goes to 1. So the output is always between 0 and 1. And this output, this one, is interpreted as a probability. So given some input x, the predicted output is actually the probability that x belongs to class 1. So the probability that the output is 1 given x and the parameters vector theta. So that's the hypothesis function. We also saw in the previous lecture the cost function minimized by logistic regression, and this is the cross entropy cost function. It's defined in this way. And we saw how to minimize this cost function in order to find the best parameters vector theta. That gives you the minimum of this function, this cost function. And just as a reminder, if y is equal to 1, right, the true output is equal to 1, then we have 1 here and we have 1 here, so this is 0. We don't have this term. So in this case, this part here is just minus, because we have a minus here, minus log h of x. And in this case, if our predicted output is close to 1, then this cost will be close to 0 because we predicted something close to 1 and the true output is actually 1, right? And when you predict something closer to 0, then this cost is very high. So the more you are closer to 0, the higher is this cost. And that's what we want because we predicted something completely different from the true output. And the other case, if y is equal to 0, in this case we have 0 here, so we don't have this term. And so this cost for classifying, or the cost for just one training example becomes this, right? And in this case, right, the true output is 0. And if you predict something closer to 1, then this cost will be high because we predicted something completely different from the true output, right? And if you predict something closer to 0, then this cost will be low because our prediction is close to the truth. So again, please check the previous video to see how to minimize this cost function and train our linear classifier, that is finding the best parameters theta. We also saw in the previous video an example of two classes which are linearly separable. So they can be separated with a linear model or a line in this case. So if this is our hypothesis function, h of x equals g of theta transpose x, right? And we are given this parameters vector theta. So theta 0 equals minus 3, theta 1 equals 1, and theta 2 equals 1. Then this is our hypothesis function, right? And if this part here, theta transpose x, is positive, right, then the hypothesis function will give us a value which is between 0.5 and 1. So the predicted class will be 1, right? And this is the case for any point which lies in this red region. And if this theta transpose x is negative, right, meaning x1 plus x2 is less than 3, right, then the predicted class will be 0. And this is the case for any point in this blue region. So this is the example we saw previously. It's an example of linearly separable case. Now, what if the two classes we have are not linearly separable, as in this example? In this case, if we use this same hypothesis function that we have here, then we will get a linear decision boundary, which is not able to separate those two classes well, because they are non-linearly separable. So the decision boundary is where this predicted probability is equal to 0.5, right? 0.5. So that's the decision boundary, and it is equal to 0.5 when theta transpose x is equal to 0, right? So theta transpose x equals 0 is our decision boundary. And this is actually the equation of a line, linear model, linear decision boundary. Because our parameters vector theta is equal to theta 0, theta 1, theta 2. And our input data, any data point x, let's say this data point is described by feature x1 and feature value x2, right? So x1, x2, plus one additional feature x0 equals to 1. So theta transpose x equals 0 is a line. It's theta 0 plus theta 1 x1 plus theta 2 x2 equals 0. So if this is our parameters vector and this is our input data and this is our hypothesis function, then we are not able to learn a decision boundary which is able to separate those two classes in a good way, right? Because we get a linear decision boundary just based on this information. And one way to get a decision boundary in this original feature space defined by x1 and x2, which is not linear, if we want to get a decision boundary in this space which is not linear, right, non-linear decision boundary, then one way to do that is just to add more features to our original features. So we get also more parameters. So our new data, let's call it z, will be a higher dimensional data than the original one, right? Higher dimensional than x. And those features that we add will be based on the original features that we have. For example, combinations of those features can be, for example, x1 squared or x2 squared or x1 times x2 and so on. And by training a new linear model based on our new data, z, then we will get a decision boundary which is not linear in the original feature space. This is illustrated here. A data point in the original space is described by two features, x1 and x2. So previously we had g of theta 0 plus theta 1 x1 plus theta 2 x2, and that's it. But now we added more features like x1 times x2, x1 squared, x2 squared. So this is a new feature that we added, x1 times x2, and it's just called z3, right? This is another feature, and this is another feature, and these are our two original features. So now our feature vector is this one, right? So we have higher dimensional data than the original one because we have x1, x2, but also new features, x1 times x2, x1 squared, x2 squared. And you can actually add any kind of features, right? Based on the two original features that we have. Now our new hypothesis function is defined as g of theta transpose z. And z is a feature vector which is higher dimensional than x, than the original one. So based on this new data, we can train a linear model, a logistic regression, as we saw in the previous lecture or previous video, right? So we can easily find the best parameters vector theta based on our new data z, based on what we studied previously in logistic regression by minimizing, for example, the cross entropy cost function. And the model we get will be a linear model in z but it's a nonlinear model in X. So if we look at Z, our model is just G of theta transpose X, right? So it's a linear model based on Z. But if we look at X, our model will be G of theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 x2 plus theta 4 x1 squared plus theta 5 x2 squared and so on. So that's a polynomial model, right? So it's a nonlinear model. And we did the same thing in some previous lecture when we talked about nonlinear regression, where we used nonlinear features plus linear regression in order to do nonlinear regression. That's the same concept. Now let's take again this example where our data is described by two original features, x1 and x2. And since we want a nonlinear decision boundary, we added two extra features, x1 squared and x2 squared. So these are two additional nonlinear features that we added based on our original features x1 and x2. So now our hypothesis function becomes this: h of x equals to g of, and g is our sigmoid function or logistic function. So g of theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 squared plus theta 4 x2 squared. And now based on this, we can define a nonlinear decision boundary. For example, if we take this as our parameter vector, so theta 0 equals to -1, theta 1 equals to 0, theta 2 equals to 0, theta 3 equals to 1, and theta 4 equals to 1, then we get this hypothesis function. And we said previously that the decision boundary is where the predicted probability is equal to 0.5, right? So h of x equals to this. And is equal to 0.5. So this defines our decision boundary. And this equals to 0.5 when this is equal to 0, right? So we have -1 plus x1 squared plus x2 squared equals to 0. So basically x1 squared plus x2 squared is equal to 1. And if you look more closely, this is actually the equation of a circle which has radius 1. So our decision boundary is actually this circle, which has this radius of 1. So just by adding these two extra nonlinear features based on our original features, we were now able to define a nonlinear decision boundary, which is a circle in this case, given this parameters vector. And please note that by varying the parameters vector or the parameters theta, right, we get a different decision boundary. So the decision boundary is a property of the parameters. It's not a property of the data. Because regardless of the data that we have, by varying theta, we get a different decision boundary. And the training data is used to fit those parameters theta, to find the optimal parameters theta by minimizing, for example, the cross entropy cost function as we saw in the previous video. Now we can use this decision boundary to make predictions. So if this part is larger than 0, so if this is larger than 0, it's positive, then we have this. So we predict class 1. And this is the case for any data point which lies in this red region, right? And if this is negative, smaller than 0, then we predict class 0. And this is the case for any data point which lies in this blue region. And you can, of course, get more complex nonlinear decision boundary, for example, by adding more features, for example, more polynomial features of higher order. So you get a more complex decision boundary.